Yeah, thanks so much, Laura, for the introduction. Yeah, so I'm going to give the second talk in this tutorial. Um, it'll be about strategizing against learners and learning in strategic environments. So I think you all have already did a great job in motivating why we care about problems where um, there's strategic settings where learning agents are taking actions. So I just think in practice today, there's many very important games that are played by learning agents. And there's all these examples. There's automated auctions. There's cases of like outsourcing your decisions to LLMs. There's distributed apps. There's things like that. Another example that I'll give right now is like, in some sense, humans are also learning agents. So in some sense, every game is played by a learning agent. Um, so what's the difference between this part and what Yoav just talked about? So Yoav gave a great talk about sort of strategic phenomena that arise when there's multiple learners in the game. Like, what can we say about dynamics? And if we're like designing these learning agents, sort of like how should we choose the learners so that the dynamics have properties we like? This talk, we're going to zoom in a lot more on like a more asymmetric problem. And the two sorts of main questions you can think about are, what should you do if you're playing a game against a learning agent? And vice versa, if you're the one designing a learning agent to be played in these games, what learning algorithm should you use? So again, there's two sorts of questions. We'll either take the perspective of one player, who we'll later call the optimizer, or the second player, who we'll later call the learner. But from the optimizer perspective, you're John von Neumann, you're playing a game against a machine. And you know this machine's running some specific type of learning algorithm, like multiplicative weights updates. And what you'd be interested in knowing is like, can you take advantage of the fact that the other agent on the other side of this game is a learning agent to improve your own utility? Is there some advantage you can eke out from the fact that they're a learning agent and not a fully rational player in the standard economic model? And there's also the flip side of this question. Like, you want to design a learning algorithm that's robust to manipulation by other rational agents. Why do you want to do this? For a bunch of reasons. Like, for one, it's hard to compute Nash equilibrium games, as we're all familiar with. For others, you might just like not completely understand the game. You might not understand your opponent's payoffs. You might not understand your own payoffs. So you want to learn these over time, but you want to learn these in a way that guarantees you good utility. And you want to do it in a way that ideally is robust to manipulation by other rational agents. So if you're trying to design a learning agent for a game like this, what learning algorithm should you choose? And what does this even mean, that you want to be robust to manipulation? Okay. So these are the two main sets of questions we're going to study. Why these questions? So I think at high level, at least for me, this was motivated by an application to repeated auctions. So imagine you're using a learning algorithm to decide how much to bid in a repeated auction. And a while back, I guess about like 5 to 6 years now, we showed that if you are a bidder and you're submitting bids by using sort of a standard online learning algorithm, something like multiplicative weights updates, there are auctioneers that can completely take advantage of this. There are weird dynamic auctions the auctioneer on the other side of you can run that extract your full welfare, that leave you with zero net utility and sort of leave them with the maximum possible utility they could hope to get in such an auction. But the other thing that this paper does is it shows that there are learning algorithms for the bidder that prevent this. And they're sort of strange learning algorithms. They're kind of reminiscent of learning algorithms that are known as no swap regret algorithms that I'll talk about a bit later. So sort of the goal of this talk and tutorial is to sort of explain sort of the theory of what's known about situations like this. And since this paper, people have worked on understanding both what happens in other settings, not just auctions, but what happens in like very general game theoretic settings. And that's sort of going to be the main focus of this part of the tutorial. So here's a very high level outline of what we're going to cover. I'll begin by going over again some preliminaries, like what does it mean to use a learning algorithm in a game? What's a no regret algorithm? What's swap regret? And then for the bulk of the game, I'm going to talk about the case of repeatedly playing normal form games, which I think is the case that we understand perhaps the best right now. Now, there's a couple things I really want to convey in this part of the talk. One is that this notion of swap regret, which I think sort of historically has been associated with convergence to correlated equilibria, has another good interpretation as a non-manipulability criterion for learners in games. If you design a learner with low swap regret, it's in some sense not manipulable. So I'll explain what these words mean in a little bit. Then I'm going to talk about why do you care about this notion of non-manipulability, and we'll talk about some recent work on designing predo-optimal learning algorithms. And by doing this, I'll also introduce like a cool technique that we call looking at the menu of a learning algorithm, lets us translate statements about learning algorithms to statements about convex sets, which are a lot easier to prove things about. And finally, I'll mention just very quickly, I think some of the most interesting open questions in the space, which is about what you actually should do if you're trying to manipulate standard learning algorithms like multiplicative weights or follow the regularized leader. So that'll be the bulk of this talk. At the very end, I'm going to talk about two things. First is what happens when you try to generalize these concepts outside of the scope of normal form games to more complex strategic settings. And the main sort of setting I'll talk about is the setting of Bayesian games, which captures this auction example I gave on the previous slide. But it also captures, we'll also talk about slightly more general sets of games. And then I'll briefly talk about some applications and work that's been done on extending this sort of idea of manipulating learning algorithms and designing non-manipulable learning algorithms to other settings. So I'll do this with a focus towards providing some interesting open questions, which of phenomena I don't really fully understand in this space. Like Laura said earlier, feel free to ask questions at any time. I don't actually have the question box popped up, but feel free to speak out loud, or Laura or someone can read the questions as they arrive. And another thing is, if you want to follow along the slides, or if I say something a bit too quickly and you want to look back, the slides should be linked on the tutorial webpage. And let me know if you can't find them, and I'll send a link. Another thing is, I'll probably go a little. A lot of the papers or a lot of the results I'll discuss will be sort of combinations of results from many papers. In most cases, I've included the relevant papers in the top left of the slide and reference list at the very end. So if you're curious where some chunk of the talk comes from, you can see it there. All right, so let's jump right into it. So let's talk about what's the game, what's learning, what are these regret guarantees. So throughout this entire tutorial, the general setup, at least for this normal form part of the tutorial, which will be the majority of the tutorial, is that there will be a repeated two-player general sum game between, between a learner and an optimizer. So one of the players, the robot, is the learner, and the other player, von Neumann, is the optimizer. And what's the difference between these two players? Not too much. So notationally, the learner has M actions. They're going to take like a mixed action every round over these M actions. They have some payoff U sub L or U sub O, depending on whether the learner or the optimizer. The main difference between the learner and the optimizer is their behavior. So the optimizer is fully rational, which basically means it can do whatever it wants. It can choose its sequence Y sub T, however it would like. Obviously, it's going to do this with an eye to maximize its total payoff given knowledge of what the learner is doing. On the other hand, the learner is going to choose its actions by running a learning algorithm, like a no-regret learning algorithm or mean-based learning algorithm. So what exactly do we mean by this? So Yoav also gave like a great overview of this, but for the sake of completeness, I'll quickly go over this again. So the basic online learning setup you can think of as relevant to this talk is the following. So every round, for again, capital T rounds, the learner is taking their mixed action X sub T, distributed over this set of M possible pure actions. Simultaneously, an adversary is going to pick some bounded M-dimensional reward vector. And then after they both do this, the learner observes the full reward vector. So we're going to operate entirely in the full information setting, and receives utility, which is sort of the inner product of their mixed action and this reward vector. And what's a learning algorithm? For the sake of this talk, a learning algorithm is just any function that maps a history of rewards, R1 through RT minus 1, to the action X sub T that the learner is going to play at around T. All right. So this is great, but in order to say more interesting things about learning algorithms, we need to impose some desired properties. So one desired property we might want to impose on a learning algorithm is that it has low regret, specifically low external regret. So what's the motivation behind this, right? So the learner ideally wants to maximize their total utility over time, but it can't truly maximize this quantity without knowing the reward vectors in advance. So we settle for something weaker. We settle for these guarantees that we call regret guarantees. So these are counterfactual guarantees that ensure we do at least as well as some class of benchmarks. The simplest possible regret guarantee, or maybe not the simplest, but one of the simplest regret guarantees you can hope to get is the regret guarantee of external regret, where you compare against the class of all fixed strategies. So what's external regret equal to? External regret's just equal to the gap between your reward, which is the sum of these xt inner product rt's, and the reward of the best fixed action in hindsight. So this maxes over all possible mixed actions. And actually, you could restrict it to pure actions and it'd be fine. And we say that an algorithm is no regret if it guarantees that this external regret quantity scales sublinearly in the time horizon t. Okay, great. So this is the notion of external regret. Can you actually get a no regret algorithm? And the answer is yes. There's many, many different types of no regret algorithms, like multiplicative weights, follow the regularized leader, replicator dynamics, gradient descent. How do they work? It's not going to actually be very important for this talk how they work, but one main trick that a lot of them use is that they approximately best respond to history. So a very useful mental model for what a lot of these things do is they look at the sort of cumulative reward so far, they perturb it a little bit, randomly, let's say, and then they pick the action that does the best against these perturbed rewards. This is exactly how an algorithm called follow the perturbed leader works. And basically all the algorithms I mentioned can be thought of as doing something like this. And because this is like a useful sort of abstraction for algorithms, we give it a name. So we call this class of algorithms the class of mean-based algorithms. So formally, what you can do is you can sort of say, okay, let's look at the cumulative reward up to time t. And we say that a learning algorithm is mean-based if the probability, like the weight the algorithm assigns to action I at time t is sub-constant. It's really close to zero whenever there is some action which historically dominates action I by at least something linear in t. So there's a couple definitions of mean-based out there. This is like a really weak definition that's good enough for everything in this talk. But intuitively, you should just think of this as any algorithm that uses the previous trick is mean-based. Like any algorithm where one action is historically a lot worse than some other action, you'll just never pick the first action. Okay, and like I said, all the previous mentioned learning algorithms are mean-based, except for maybe some variants of gradient descent. And I'll mention this briefly towards the end of this talk. Okay, so far we've talked about low external regret algorithms, and we've talked about low these mean-based algorithms, which is maybe one way you can get low external regret in a lot of cases. The other important regret guarantee to know about for this talk, because this is sort of the main thing I really want to, the main object I really want to discuss, is this regret guarantee called no swap regret. So what is swap regret? So just as external regret was a regret benchmark that compared against all fixed actions, swap regret's a regret benchmark that compares against all fixed mappings of actions to actions. So what you do is instead of competing with just the best fixed action like before, you compete with the best mapping pi star, or just pi, I guess, that when you apply to your sequence of actions, gets the maximal utility. And I think the more convenient way to word this or to think about this is that you should sort of think that if I have low swap regret, I should not be able to improve my utility very much by playing, let's say, action B everywhere I used to play action A. So if you've been playing rock, paper, scissors a lot, there shouldn't be like a case where if every time you played rock, you instead of played scissors, you start winning omega of t more games. All right. And just as before, for no regret, we say an algorithm is no swap regret if it guarantees that the swap regret scales sublinearly in the time horizon. All right. So this is slightly a weird, this is definitely a weirder notion of regret than external regret. How do you get it? You also have to do something a little weirder than for no external regret. So there's basically two classes of ways I know to get it right now. So one is these sort of fixed point methods, of which Blumenser is one example. So what you can do is you can construct this Markov chain over no external regret learning algorithm instances and play a stationary distribution of this. Don't worry about understanding what I'm saying. If you haven't seen this before, it's not going to be relevant for the rest of the talk, but the point is there's some cool fixed point algorithm you can do that gets no swap regret. Very recently, there have been like two new very similar algorithms concurrently proposed that don't explicitly have this fixed point, that do something based on more of like a tree decomposition of time. But in either case, you have to do something pretty clever to get no swap regret. Which maybe begs the question, like, why should we care about swap regret? Like, why do we care about having low regret with respect to this mapping of what we did instead of like just fixed benchmarks? And so historically, the reason for this was that there's a class of equilibria, an equilibrium notion called correlated equilibrium. And it's known that if you're in a game and every player in the game is running a low swap regret algorithm, all the learners will, on average, over time, converge to one of these correlated equilibria. So this is a very good reason. There's like some reasons. I think the original definition of correlated equilibrium was proposed by Aumann like maybe 50 years ago, why you should care about this. But I'm not going to talk about this at all in this talk. Instead, in this talk, I'm going to talk about other reasons why you should care about swap regret, especially in strategic settings. All right, and so there are two big simplifications I'm like going to make throughout this that I claim don't really change anything, but it just makes things a lot easier to talk about. So first, everything I talk about in this talk will be in the deterministic, full information, fractional setting. So all these learning algorithms are just playing mixtures. They see all the rewards. They sort of like deterministic maps from the past to the next action. And I claim that sort of nothing important changes with partial information or banded feedback. And one reason for that is the second simplification, which is that really I'm not going to talk at all about specific sublinear terms. Like I'm not going to talk about rates of convergence or regret bounds. And the reason for this is that instead, most of the results here are actually going to be concerned with linear terms in T. Like we're going to see cases where when in the learning algorithm is exploitable, it's actually exploitable by like terms that are linear in T. Like you can get linear in T more than you could get against some other learning algorithm, for example. Okay, great. So I think I'll jump right into the bulk of this talk, which is about normal form games. And more specifically, sort of this question of how should you play against a learner if you're playing a repeated normal form game against a learner? So recall, you have this, you have a two-player game. One of the players, the learner, has this utility U sub L, and they're playing against an optimizer who has this utility U sub O for capital T rounds. And the learner is going to be running some no-regret learning algorithm. Think of it as multiplicative weights, or follow the regularized leader, whichever you'd like. And the main question we're interested in, at least to start, is what should the second player, what should the optimizer do to maximize their total utility? Okay. So there are sort of two classes of things the optimizer can do. The first option is say, all right, I'm not sure exactly what this learner is going to do, but I'm going to like look for a good fixed strategy. So the first option is they find a good fixed strategy for themselves. This is like some distribution over their n pure actions. And if the learner is running a no regret learning algorithm, then the learner is going to quickly learn to best respond to this action by playing something which maximizes their utility. So thinking ahead, the optimizer will choose their best fixed strategy Y star, and the optimizer will get some sort of constant utility per round, this like U sub O of X star comma Y star per round. And this quantity has a name. This is called the Stackelberg value of the game. So again, sort of reiterating, the optimizer plays Y star, which is sort of the Y star that maximizes this U sub O of the best response to Y played by the learner, comma Y, which is what the optimizer is playing. And this is one way to define the Stackelberg equilibrium of a game. And if the optimizer does this and chooses their best Y, their asymptotic per round utility will just be exactly the Stackelberg value of this game. And there's some type breaking details in these definitions, but don't worry too much about them. They don't really matter too much for most games. All right, and we'll call the Stackelberg value Stackelberg of G for now, because this will be an important quantity in what's to follow. Okay, so this was option one. What's the other option? The other option is the optimizer can do something else. The optimizer can play a strategy that changes over time. And you can ask, can the optimizer ever really do better than this fixed strategy by playing a weird dynamic strategy? And the answer turns out to be yes, even for very, very standard learning algorithms like multiplicative weights updates, or in fact, any mean-based algorithm. So that's what I'm going to show right now. I'm going to show how if the learner is running a mean-based learning algorithm like multiplicative weights, how an optimizer can get more than their Stackelberg value. So here's a very explicit game with 2 optimizer actions, N and Y, and 3 learner actions, A, B, and C. You can check, it's a small computation, that the Stackelberg value of this game is 1/3. The optimizer can play something like 1/3 of N plus 2/3 of Y, and the learner will best respond by playing C. And if the optimizer does this, they'll get, for all capital T rounds, they'll get something like T/3 utility, and the learner will get something like T/6 utility. Okay, great. And then one note is that this example actually comes from a cool principal agent application to designing contracts for learning agents. But the details of that aren't really important. That's where these utilities come from. Somehow the optimizer is trying to persuade the learner to take some effort on their behalf. Okay, but you can think of it just as completely an abstract game. What can the optimizer do that's better than just playing this fixed strategy? So there's a couple things, but one thing they can do is they can play their Stackelberg strategy for the first T/2 rounds, like before. And then like before, the learner will best respond by playing C. And then the interesting thing is for the last T/2 rounds, they're just going to play action N. And you'll see that action N gives the optimizer a lot of utility if the learner plays B or C, but it's actually bad for the learner. The learner gets negative utility if the optimizer plays action N and they play B or C. So now you can ask, like, what's going on here? Why is the learner playing best responding with action B instead of action A? Because action A is the action that gives them the best utility if the learner is going to, if the optimizer is playing action N. All right. And the reason is really because of this, what these mean-based learning algorithms do. Remember that these mean-based learning algorithms sort of just pick the action with the best cumulative utility over time. So if you graph these like cumulative utilities, action A stays at 0. Action B and C both do pretty well for the first half of the game, while the optimizer is playing their Stackelberg strategy. But then once the optimizer switches, there's some momentum built up. The learner does not like immediately realize that the optimizer switched to only playing action N, and actions B and C both still look pretty good in hindsight. And it turns out that action B is the optimal action for the second half of the game. And anyways, by doing this, the optimizer gets a little bit more utility than they would have gotten by just playing the Stackelberg strategy. And you can actually show that the learner really loses out by doing this. The learner used to get T/6 total utility from this partnership. Now they end up with like 0 utility because they're just losing utility for the second half of the game. Okay, so this is one example where things can go wrong. I see there's a question. Is knowing the horizon crucial, or can we have some anytime manipulations against mean-based learners? All right, that's a very good question. This is actually a question which we study a little bit in this second paper on the top left. I think, I don't know, in this example, it might not be possible to do if you don't know the horizon, but there are games where you don't need to know the horizon to exploit a mean-based learner. And the idea there is like, you can just go in cycles. Like you can, break your time horizon into like 100 blocks of size T/100 and do some like weird manipulation like this in each block. And these types of things can still outperform the Stackelberg strategy. So in some games it's crucial, but like in some, there's still examples where you can manipulate a mean-based learner without knowing the time horizon. Great question. Okay. But anyways, here's one example where the learner really, maybe preferred to do something different aside from playing a mean-based learning algorithm. So let's try to characterize this a little formally. So we're going to characterize the notion of non-manipulability for learners. And we'll say that a learning algorithm is non-manipulable for if for any game G. If a learner uses this learning algorithm to select their actions, then the optimizer can't benefit by doing anything strange and dynamic. The optimizer gets no more than their Stackelberg value per round. And I'm calling it non-manipulable here. In some other previous work, it's been called robustness to dynamic play of the optimizer. Basically, there's no benefit to doing something strange and dynamic. And the previous example sort of shows that all mean-based algorithms are manipulable. Okay, so what algorithms are not manipulable? And based on what I said earlier about swap regret, you might guess that, yeah, it's exactly the set of no swap regret algorithms. So sort of the main theorem, maybe this is like one of the main theorems I'd like you all to take away from this tutorial, is that a learning algorithm is non-manipulable in the sense if and only if it's no swap regret. So this characterization of having no swap regret is like an equivalent characterization of exactly which learning algorithms are non-manipulable. And I sort of like to think of this as an alternate sort of like utility theoretic interpretation of no swap regret learning instead of like a more equilibrium-based interpretation. So I'll briefly mention how you'd prove this type of thing, but I won't go into many details. So there's sort of two parts to this proof. First, you would want to show that any no swap regret algorithm can't be manipulated. And the second is you'd want to show that if an algorithm sometimes gets high swap regret, then it can be manipulated, at least in some game. Obviously, there's some games where there's no manipulations possible, like where the learner has only one action. Okay, so how do we show that no swap regret implies non-manipulability? So imagine a setting where the learner has played some sequence of actions, the optimizer's played some sequence of actions, and the learner was running a low swap regret algorithm. So this sequence of actions, pairs of sequences of actions should have low swap regret. What we like to show is that the optimizer is getting at most the Stackelberg value of the game. So the main idea is we're going to look at the set of rounds where the learner has played a specific action, let's say action I. Since the learner has no swap regret, the learner must be best responding to the optimizer on these rounds, and therefore the optimizer must be getting at most the Stackelberg value per round on these rounds. And I think it's a little bit easier to sort of see if you like look at sort of a drawn out example. So like imagine this is what the trajectories of play looked like. So the learner played the sequence of actions A, B, C, C, A. They don't in general have to be pure actions, but in this case they are for simplicity. The optimizer played some other actions, these like Y sub T's. And let's just look at all the rounds where the learner played action A. So the learner, what we can do for these rounds is we can look at the average action played by the optimizer on these rounds, this Y sub capital A. And let's think about the properties of Y sub capital A. So in particular, if capital A is not a best response to Y sub capital A, then the learner has swap regret. Just by the definition of swap regret, they could swap playing action A to some other action, the actual best response to Y sub A, and they would gain a bunch of utility. So therefore, since the sequence has low swap regret, A must be the best response or close to best response to Y sub A. And therefore, the average optimizer utility in these rounds is of this form. It's of the form, the optimizer utility of a best response to Y sub A comma Y sub A. And this is at most the Stackelberg value, because the Stackelberg value is just a maximum over terms that look like this bottom left term. Okay. So it's a very simple proof. It's almost like tautological that no swap regret means non-manipulable, but I think it's a nice way to think about no swap regret. So there's the other half of the proof, of course, that if you have high swap regret, then you're manipulable. And the idea here is that what you want to do is you want to design a game where if the learner is running this high swap regret algorithm, then the optimizer can get linear more utility than the Stackelberg value. All right. And it turns out that you can construct a game with where the Stackelberg value of the game is 0, but where like the reward of the optimizer is equal to the swap regret of the learner. So there's like an explicit construction. You can find it in this paper. But there's an even simpler proof that I'm going to mention briefly later via menu. So I'm not going to show you guys the construction for this. Okay. This may be a good place to, well, okay, this is a good place to pause if there's any questions. not, I will continue to sort of the second chunk of things I want to say about normal form games, which is, why should we care about this notion of non-manipulability? So if you looked at the definition earlier, you might have noticed there's something a little weird about this notion of non-manipulability. And it's that, so in some sense, we're taking the perspective of the learner, because we want to say we don't want the learner to get manipulated. But the definition basically says that we're going to design an algorithm for the learner that guarantees that the other player doesn't get a lot of utility. And this is like a little counterintuitive. This definition is a little weird. Why should the learner care about capping the value of the other of the other player, the optimizer? And you can ask, can being manipulated actually be good for the learner? And sort of this even more general question of like, is it even good in general to like run these no swap regret or no external regret algorithms if you're learning in games, if you want to just like if the learner just wants to optimize their own utility? So the answer to the previous question on the previous slide, and this question is like sort of murky and kind of negative. So there definitely exist mean-based learners whose utility improves if the optimizer dynamically manipulates them. So they get some utility under the Stackelberg strategy of the game, but they get even higher utility if the optimizer takes advantage of the fact that they're mean-based. So you can interpret this as maybe evidence that you should run these mean-based algorithms. But of course, there's also examples that go the other way, like the examples I showed you earlier. And there's other like things that add to this confusion. So for example, if you have a game, so this is sort of like the metagame setting that Yoav was talking about earlier. If you have a game where you have two no swap regret learners are playing against each other, sometimes these no swap regret learners can benefit by deviating to either their Stackelberg strategy or even to just playing regular no external regret algorithms. So it's like, there's definitely a situation, it's hard to say that no swap regret is strictly the best thing to do in every single situation. So how do you reconcile this with the fact that it seems like no swap regret and non-manipulability are nice constraints to have in games? The main idea that I'm going to talk about in the next few minutes is that if you relax your notion of being a good learning algorithm to some sort of Pareto dominance or Pareto optimality instead of strict optimality, again, you see that low swap regret algorithms have very nice properties. So the setup here is going to like change a little bit, not significantly. It's basically the same setup. So again, we have a learner playing a game. They know their own payoff, usable, but not the optimizer's payoff, usable. This is sort of the standard learning algorithm setting because your learning algorithm should really only use your own rewards and not the other player's rewards. And you can ask what learning algorithm should they run. And of course, there's this problem I just mentioned where a specific learning algorithm might be good against one optimizer payoff, but bad against a different optimizer payoff. So the solution here is to sort of relax the notion of what the best algorithm is to something we call asymptotically Pareto optimal. Okay, so there's a definition of asymptotically Pareto optimal above. I think intuitively you should think about it as follows. Like we say that one algorithm is Pareto dominates the second algorithm if the learner never suffers worse utility. Let's say algorithms A and A prime. We say that A dominates A prime if the learner never suffers significantly less utility by running A than A prime. And there's some case where the learner gets a lot more utility by running A than A prime. So this is what it means for A to dominate A prime. And of course, if A is not dominated by any algorithm, it's optimal, Pareto optimal. Okay, so time will go a little quickly here, but the main sort of takeaway from this section is any no swap regret algorithm is Pareto optimal for any learner payoff. And if you've been following the definition closely, you might be like, all right, that's fine, but this Pareto optimality notion is like a little bit weak because you only have to be better on like a single payoff in order for you to not be dominated by another algorithm. So maybe every learning algorithm is Pareto optimal. But no, this isn't the case. And there do exist cases, like games, where any instantiation of FTRL is predominated. And probably you can straighten this to any mean-based algorithm is predominated. So this is sort of saying that no-swap algorithms are special, not just because they're non-manipulable, but also they're, like, in some sense, they're predo-optimal in a way that no external good algorithms in general are not. And I do want to say some things about the main technique we use to prove this type of fact, because I think it's a technique that's useful not just for proving facts about this notion of predo-optimality, but also for proving a lot of other facts about learning algorithms in strategic settings. And this is a general method for translating statements about algorithms to statements about convex sets. And we'll call these convex sets asymptotic menus. Okay, so what is an asymptotic menu? So first of all, I'm going to talk about a correlated strategy profile, which is a concept that also comes up if you know about things like correlated equilibria or coarse correlated equilibria. But basically, let's say you've actually played the game for capital T rounds. The learners played these actions. The optimizers played these actions, these y sub t's. The correlated strategy profile corresponding to this transcript of the game is an element of the tensor product space of these two simplices, the M simplex and the N simplex. That's just sort of like the average of xt tensor yt for all xt comma yt in the game. So this is like an m times n dimensional vector. You just think of it as it's sort of, you know, the joint probability matrix of playing every pair of actions. Okay, so this is a CSP. What is the menu of a learning algorithm? So there's some details here, but I think the way you should think about the menu of a learning algorithm is the menu of a learning algorithm contains all CSPs that are implementable against the learning algorithm. So if you got to choose the optimizer's behavior and you could do whatever, what's the set of CSPs you could cause the learning algorithm to end up at? And there's some, like, we take the limit as t goes to infinity and ensure that, like, you have to get these for every, like, sufficiently large t. But this is what the asymptotic menu of a learning algorithm is. And just to sort of make sure everyone understands, let's compute this menu for two very simple learning algorithms. So first we'll look at the learning algorithm, in quotes, that always plays just one action. So throughout this and the next example, we're just going to look at a game where both the learner and the optimizer have two actions. The learner can play action R or S, and the optimizer can play action X or Y. All right. So what happens in this example? The learning algorithm always plays action R. What CSPs can you implement against this learning algorithm? Well, what you can do is, as the optimizer, you can always play action X. You can get this CSP R tensor X. You can also always play action Y and get the CSP R tensor Y. And you can also do any convex combination of these two things. For any mixed strategy little y that you can play, you can get capital R tensor little y. So the menu in this case is this convex set, which is just this line segment connecting R tensor X and R tensor Y. All right, very simple case. Here's a slightly more complicated case, but not much more complicated. Now let's look at a learning algorithm A that plays action R on odd rounds and action S on even rounds. Cool. So what does the menu look like in this case? So I think I'm not going to go through the math to explain why it's this, but if you don't understand the notion of asymptotic menu, I think it's worth pondering this example for a little bit. So what does the menu consist? The menu consists of all points of the form 0.5 times R tensor Y sub R for some Y sub R in the N simplex, 2 simplex in this case, plus 0.5 times S tensor Y sub S for some other mixed strategy of the optimizer Y sub S, right? And geometrically, this menu is just this two-dimensional square or parallelogram with these extreme points. Okay. And then the intuition is sort of just that you can play Y sub R on odd rounds and Y sub S on even rounds and get a point like this, and there's nothing else you can really do. Okay, so hopefully this gives you all some intuition for what a menu of a learning algorithm looks like. What else can we say about menus? So we can characterize which convex sets are valid menus that correspond to real learning algorithms. And you can characterize this via a cool technique known as black hole approachability. The actual characterization is very simple. Basically, any convex set S that contains a point of the form X tensor Y for each Y in the n-simplex is a valid menu. So you basically just need to have a bunch of different product distributions in your menu, one for each possible marginal of the optimizer. So this example, the line segment connecting R tensor X and R tensor Y is a valid menu. This one connecting R tensor X and S tensor X is not a valid menu because there's nothing supported on Y. Similarly, this like single point, not a valid menu. So this is great because now we can sort of just translate questions about learning algorithms to questions about these convex sets that we have like a nice geometric characterization of. And okay, so what menus do we really want to say things about? So there's two classes of sets we want to talk about through this like menu theoretic language. One is menus for specific specific types of algorithms. So for example, if we have a specific no regret algorithm, a no swap regret algorithm, or mean-based algorithm, we might care about the menu of that algorithm. The other sets we might care about are menus that correspond to regret constraints. So another nice thing about looking at things in this menu space is that you can also define regret and swap regret entirely in this menu space. So knowing the correlated strategy profile that corresponds to a transcript of the game is sufficient information to compute the regret of the learner in this game and their swap regret. So we can define sets like this no regret menu, which contains all the points which have 0 external regret for the learner, and also the no swap regret menu, which contains all these points which has 0 swap regret for the learner. And here the 0 is sort of like asymptotic, so it really contains a set of points which have little o of t regret and little o of t swap regret. Okay.
Jon?
Yeah.
Could you comment briefly on why calling those menus? Why do you call those menus?
Okay, great. So there'll be an answer on the next page, partially.
Oh.
But one reason is that these two sets do satisfy the characterization of menus. So there are learning algorithms which actually have these sets as menus. So there is like a learning algorithm, like a generic no regret learning algorithm whose menu is this entire no regret set. And there's also a swap regret algorithm which has this no swap regret menu as this as their menu. Yeah, great question. But the second reason is that, again, no swap regret's a little special. So the no swap regret menu has a bunch of nice properties, but basically it is inclusion minimal. So every menu that corresponds to a no regret, let's just say algorithm, every menu corresponding to a no regret algorithm contains the no swap regret menu. And yet there's no valid menu that's strictly contained within the no swap regret menu. And finally, you can also like have this very nice explicit characterization of the no swap regret menu as the convex hull of all of these Stackelberg points we saw earlier. So all these product distributions where the optimizer plays some strategy Y and the learner plays a best response to Y. So this is like an explicit characterization of this no swap regret menu. And this has a couple of consequences, but I'll just point out two of them, which are particularly nice. So the first is that every no swap regret algorithm actually has the same asymptotic menu, and it is this no swap regret menu. So this is really the reason why I call it the no swap regret menu, because it's actually the menu of every single no swap regret algorithm. This is not true for no external regret. No external regret algorithms can have different menus. The second consequence is that this equivalence I described earlier, this fact that no swap regret's equivalent to non-manipulability, this also follows from this theorem, from the fact specifically that's the convex hull of all Stackelberg points. So I won't go through why this is true, but basically optimizing over MSR is basically the same thing as the optimizer optimizing against a no swap regret algorithm, and they get exactly their Stackelberg value. Okay. Maybe in this time I'll skip this. What I want to say here is that, so I mentioned this notion of Pareto-optimality earlier. Pareto-optimality translates to like a very nice geometric constraint when you translate it from algorithms to menus. It's basically something like, I have these two convex sets. I like look at an extreme point in some direction, this like red direction, which corresponds to the optimizer utility. And I want the learner's utility of one of these points to be bigger than the learner's utility of the other points. Or I can ask like, when does a convex set have this property that every extreme point in some direction has a bigger x coordinate than the extreme point in another direction. So I'll skip this in the interest of time, but feel free to take a look at the slides. But a consequence of this is that you can now reduce this theorem about pre-optimality of algorithms to this theorem of proving facts about convex sets living inside the m times n simplex. And that's what this paper does. You can give a characterization of all these no-regret menus that are polytopes. So we don't have a completely full characterization, but we have enough of a characterization to prove this theorem. I think one interesting open question here is to actually give a full characterization of every single pre-optimal menus, not just menus that are no regret, and not just menus that also are polytopes, that menus that can be like other arbitrary convex sets with infinitely many extreme points. Okay, so some takeaways from the normal form case. So I think there's basically big difference between no regret learning and no swap regret learning in these strategic environments where you're learning in a repeated normal form game. No regret learning can be manipulated. Different no regret algorithms can have different menus. And no regret learning is sometimes predo-dominated. There are situations where you can do strictly better against every single optimizer by changing the algorithm. On the other hand, no swap regret learning is not manipulable. All these no swap regret algorithms share exactly the same menu, and no swap regret learning, these no swap regret learning algorithms are predo-optimal because they all have the same menu, and it's predo-optimal menu. And I sort of like to think of this as swap regret seems to be the correct regret notion for learning in games. You may or may not agree, but I think this is hopefully at least somewhat compelling for thinking about it this way. And the second takeaway I wanted to say is that this technique of thinking about the menu of a learning algorithm is pretty powerful for understanding learning in games. It can tell you basically all the results I mentioned in the previous slide, and they translate questions about complicated objects like learning algorithms to questions about convex sets, which are a lot simpler. They don't capture everything. So they completely ignore these sublinear terms. They don't capture dynamical information like last iterated convergence, chaotic dynamics, but they capture like a wide range of utility theoretic questions about a learning algorithm's behavior. Okay. The last thing I want to say about normal form games before we sort of leave the realm of normal form games is to go back to this original question of manipulating mean-based learners. So you can ask, what if the learner actually is running a mean-based algorithm? What can the optimizer do? And the short answer is we know very little about this. We know that you can't do better than Stackelberg. Like sometimes it's not manipulable for certain classes of games. For example, if the game is zero sum or constant sum, a lot of these notions collapse. Also, if the game has only two actions for the learner, you can't do better than Stackelberg for the reason that, in this case, external regret and swap regret collapse. If the learner only has two actions, having low external regret is enough to have low swap regret. And there are some explicit games based on some instances that come from contract theory where we can compute the optimal dynamic optimizer strategy against a learner, then it's like a non-trivial strategy. It's doing something better than just playing the Stackelberg value. But we're very far from a complete understanding of this problem. So the sort of second open question here is, if I give you a game, can you provide an algorithm that decides whether the optimizer can do better than just playing the Stackelberg strategy every round against a mean-based learner? And if so, how much better? Like, what should they do? What's the optimal per round utility they can get up to maybe some additive epsilon t? And then one interesting thing here is I don't even know a finite time algorithm for this question, like whether it's computable. Almost definitely some sort of algorithm exists, but it's hard to put a bound on like the maximum time horizon you need to consider, for example. And another rephrasing in this menu language is, can you compute the mean-based menu for a game? And we say a little bit about this in this recent paper. Okay, so running a bit low on time. Maybe this is a good place to stop for questions, and then I will say just a couple things about Bayesian games and beyond and other applications.
Yeah, I have a question. So about the basic setting, the assumption is that the repeated game in every round, the game is exactly the same, right? Between the optimizer and the learner, like it's the same utility for every pair of actions. I'm wondering if the results can be adapted to a setting where the state of the game changes between rounds. I'm thinking of like a Markov decision process sort of setting where there's a state and the sort of per round utilities depend also on the state of the game, and the state depends on the previous actions.
Yeah. No, that's a very good question. Like whether these extend to like Markov games or these types of stateful games you mentioned. The short answer is I don't know. I don't know anyone who's like really studied this type of question. What I will go through very quickly in a second is an extension to like Bayesian games, which have some amount of private information, but basically, as soon as you get outside of, or sorry,
the reason I was asking is, at least in one of the examples, the motivating applications that you gave, the blob 4844 blob posting games that you had in your first slide. I mean, that's an example of a game where the state is really important for the dynamics. And so I think it's very relevant.
Yeah.
And yeah, I was wondering if anyone, like if there's any literature on this, like I have no idea, so.
No, I think that's a great question. I think the closest thing is that there's one paper which studies auctions, but where like the values are generated adversarially, so the values can change over time in an adversarial way. But yeah, I think people have nowhere near any understanding for that question. Good question.
Thanks.
All right. Any other questions? Okay. Since we only have 4 minutes, I'm going to go through this section on Bayesian games really quickly. Feel free to look at the slides at your leisure. But the main things I want to say are that the original motivating examples for this line of work were in fact Bayesian games. This auction example, there's private information the learner has, which is their value for the item every round. And the learner is actually doing some sort of contextual learning where they see the value every round and they want to like choose their action based on that. So you can ask, you can define Bayesian games formally and contextual learning formally, and you could ask, what is the correct notion of swap regret in contextual, in Bayesian games and contextual learning? And you know, ideally, we'd want a similar type of result that we had for normal form games where no swap regret is equivalent to non-manipulability. But many of like the very straightforward things you'd think don't work. Like you can't just do no swap regret per context. There's other things which don't work too, like this notion of linear fear regret or extending what was done in the original auction paper. So I think at this point, we do know what the correct notion of swap regret should be. Is this notion of polytope swap regret. So feel free to look through these slides to see how it's defined. It's definitely like a weird notion of swap regret. Basically, it says something like you can think of a Bayesian game as you're taking actions in a product of a bunch of simplices. Every round, you're playing a point inside this weird polytope. But when you want to apply a swap function to it, you can't directly swap this point to like any other point. You want to swap the pure strategies. You want to swap the vertices. So what you do is you let the learner decompose their action into vertices however they would like. And then the adversary applies the worst case swap to the vertices. And then the composition of these two steps maps each sort of pure action or maps your original action, which was like a weird mixed action, to a new mixed action by going through this decomposition to pure actions. So it's now known that for Bayesian games, this is the correct notion of swap regret in the sense that its learning algorithm is non-manipulable if and only if it has low polytope swap regret. But you can ask this question for even more general classes of games. specifically for a class of games we call polytope games. And I think one very interesting class of polytope games, where, as far as I know, people haven't really thought about this too much, is the class of extensive form games. It's had a lot of applications to things like designing learning algorithms for games like poker. So it's a good question whether polytope swap regrets the correct notion of non-manipulability in these types of games. There's also now computational questions. So I do not know anything anywhere near efficient for optimizing this notion of swap regret, which I didn't really define for you guys. But you can ask, are there efficient algorithms that minimize this type of swap regret? And if not, what types of swap regret should you settle for instead? And what type of manipulability properties do you get from these notions? All right. And then quickly, I just want to mention that people have sort of like extended this framework to a bunch of other practical settings. So, beyond the work on auctions that sort of motivated this line of work, now people have thought about this problem of playing against learning agents in contract settings, principal agent settings, Bayesian persuasion settings, these like fair allocation settings, and there's some tenuous applications in forecasting and calibration. What I want to do is I just want to go through some of these works in auctioning, to mostly as a way to mention a couple interesting open questions of things that we don't generally understand, but we understand specifically for the case of auctions. So one of these things is something I mentioned very briefly, which is Bayesian learning without a prior. So the original auction paper showed that you can extract a buyer's full welfare if they're running a mean-based algorithm. One thing that was done shortly after that is, it was shown that you can do this even if the buyer's values are adversarial, not independently sampled from a known prior every single round. So I think an interesting open question here is to understand what happens in general Bayesian games when types are chosen adversarially, and is this polytope swap regret notion still the correct notion of swap regret in these games? Secondly, very interesting generalization. This is learning when there's multiple agents, when there's in multiplayer games where there's more than just two players. So again, the original auction paper showed that you can extract a buyer's full welfare if they're running a mean-based algorithm, but assume there's a single buyer bidding against a single seller. Very recently, it was shown that you can do this even if there's multiple buyers. You can still extract the maximum welfare of this game and getting the expected max of utilities even. So again, you can sort of ask, like, what is the correct notion of swap regret? What's the correct type of learning algorithm players should run in multiplayer games? Is there a good theory of non-manipulability and Pareto-optimality for these games? And finally, I think this is maybe like the most one of the most interesting directions for me, because it was really surprising that this worked, which is that, so like I mentioned in the original auction paper, there's also a learning algorithm, a kind of weird learning algorithm that was no swap regret-esque, even though it didn't minimize any explicit notion of swap regret, that prevented the optimizer, the auctioneer, from getting more than their Meyerson revenue, which is basically the Stackelberg value in this game. And what was shown really recently is that you don't actually need to run this strange no swap regret-esque learning algorithm. Instead, you can just run some specific form of eager gradient descent, and you still get this non-manipulability property. You still get the fact that the optimizer can't get more than the Meyerson value. And I think this means that, now it's interesting to go back to the original setting of normal form games and just ask, in which games does eager gradient descent prevent the optimizer from getting more than Stackelberg? Like, what is the menu of eager gradient descent? So we know that eager gradient descent is not a low swap regret algorithm. You can force it to get low swap regret, so there are games where you can exploit it. But clearly, it's in some sense harder to exploit, harder to manipulate than the class of mean-based learning algorithms. All right, and just to conclude, reiterating like the takeaways I shared earlier, there's a couple of ways in which swap regret's the correct notion of regret for strategic settings. I think menus are like a powerful tool for sort of like understanding these questions about what notion of regret's the correct notion. What should you do in different strategic settings? And there's a bunch of open questions about what the correct generalizations of swap regret are to like more general strategic settings. There's even this question of whether it's polytope regret in general. And then there's also many other open questions. So, connecting back with some of the things Yoav said, like, can we use the insights from this line of work to understand how to do mechanism design for learning agents? Can we understand metagames through this framework? Like, can we understand dynamics, or do low swap ordered algorithms have nicer dynamics than low external ordered algorithms? These are all, I think, pretty interesting questions, and I think there's still a lot of work to do. All right, so apologies for going a little over. Thanks for listening to the talk. Here are just some of the references. The ones in red are papers that I believe are going to be presented at EC this year. So keep an eye out for those if you're attending in person. And yeah, thanks again.